In this section we look at using 2 by 2 matrices to solve linear simultaneous equations. So here we have an example where we're given two linear simultaneous equations and we're asked to solve. Now we could apply the traditional approach to solving simultaneous equations. So we could simply multiply the second equation by, or the first equation by 2 to bring the x's to be of the same value. And then when we subtract the two equations, the x's cancel and we get 4y equals 12, y is equal to 3. So we could then substitute the value of 3 back into either of the equations. So let's take the second equation here and putting y for 3, we get 4x plus 2 times 3 equals 10, 4x plus 6 equals 10, 4x equals 4, and x is equal to 1. So using the traditional method, we find that x is 1 and y is equal to 3. So now let's have a look at the same question, but this time we'll try to solve it using matrices. So as we saw before, if we have a linear equation like this, we can take the coefficients of the x and y's and write them in matrix notation as follows. So this same equation can be written in matrix format, so the 2 by 2 matrix multiplied by xy equals 11, 10. Because if we multiply that out, we get 2 times x plus 3 times y equals 11. And 4 times x plus 2 times y equals 10. Right, so to solve this, we need to multiply both sides by the inverse of this 2 by 2 matrix. Now, before we do that, we need to calculate the determinant of A. So let A be equal to the matrix 2, 3, 4, 2. And if you remember, to get the determinant of a matrix, we get the difference between the product of the diagonals. So in this case it'll be 2 times 2 minus 4 times 3, which will be 4 minus 12, which is minus 8. So now that we have the determinant, we should be able to calculate the inverse of A. Now again, if you remember, if we have a matrix which has the element A, B, C, D, the inverse can be found by interchanging A and D and changing the sign of B and C, and then multiplying the new matrix by the reciprocal of the determinant of A. So if we apply that logic here, we could change or interchange the 2's, which will just give us the 2's back again, change the sign of the 3 and the 4, so we get minus 3 and minus 4, and multiply the resulting matrix by the inverse of the determinant. So now that we have the inverse, we can now go and solve this equation. So what we do is we multiply both sides of this equation by the inverse of A. So we multiply the left hand side by the inverse and then multiply the right hand side by the inverse. Now when you multiply the inverse of any matrix by the original matrix, you just get the unit matrix. So we could replace these two terms here by the unit matrix, and on the right hand side we need to multiply this 2 by 2 matrix by the column matrix. So we do that by using the normal multiplication rule. So this will give us 2 times 11 minus 3 times 10, and then the second row by the first column will be minus 4 times 11 plus 2 times 10. So if we work this out, we get 22 minus 30 and minus 44 plus 20. And further simplifying, 30 from 22 is minus 8 and 20 minus 44 is minus 24. So if we divide it minus 8 or multiply this column matrix by minus 1 over 8, we get 1 and 3. So therefore xy is equal to 1 over 1, 3. So therefore x equals 1 and y equals 3, which is the same value that we had when we used the traditional approach. Now here's a question that you could try yourselves. So again, you're given two linear equations with two unknowns, and you're asked to find x and y. And the answer is x is equal to 3 and y is equal to minus 2. So pause the video and have a go at that. Now let's have a look now at some applications or real engineering applications of using matrices. So here's a question where we're told that a force system was analysed by resolving the horizontal and vertical components of the forces. And this gave the following linear equations in terms of F1 and F2, and we're asked to find F1 and F2. So really this is just solving these two linear simultaneous equations, which is similar to what we just did. So let's have a go at this. So once again, we can write the two linear simultaneous equations in matrix notation as follows. So we get a new 2 by 2 matrix, 6 minus 1, 5, 2, multiplied by xy equals 5, 7. So once again, we need to get the inverse of this matrix and multiply both sides by this inverse. So to do that, we need to get to the determinant of the 2 by 2 matrix, which is the difference in the products of the diagonals, which will be 12 minus 5, which is the same as 12 plus 5, which is 17. And then we get the inverse by interchanging a and d. So this becomes 2 and this becomes 6, and then changing the sign of minus 1 and 5, so we get 1 and minus 5. And we multiply the new matrix by the reciprocal of the determinant. So now that we have the inverse, we can multiply both sides of the equation by the inverse. So that will give us the following equation. And again, the inverse times the matrix will be just the unit matrix. So we can replace this section here by the unit matrix. And then we multiply the right hand side. So again, the first row by the first column will be 2 times 5 plus 1 times 7. And then the second row by the second column will be minus 5 times 5 plus 6 times 7. And this works out to be 10 and 7, which is 17. And minus 25 from 42 is 17. So 17 into 17 for both x and y gives us 1 and 1. So therefore x is equal to 1 Newton and y is equal to 1 Newton. So here's another question that you could try. And again, this time we have two linear simultaneous equations which describe the current flowing in an electric circuit, and you're asked to calculate I1 and I2. So have a go at that and see can you get that I1 is minus 1 amp and I2 is 2 amp.